So these are the first two questions from the step 3 hyperbolic functions booklet. We've got a lovely question here integrating some different hyperbolic functions. And then this is like borderline the most fun I've ever had doing a step question. This was just brilliant. Anyway, so let's get into it. Let's start with this first one. Show this integral here is the first thing we're being asked to do. So, okay, clearly we need to make a substitution, I guess, and we'll make a substitution u equals cosh x. Usually this is the case when you see a lone sine or cos or cosh or sinh on top to make the substitution, because then, of course, when you differentiate like this and you divide over here, it will cancel with the one up there. So that works quite well. Here, I'm just saying when x is a, that means u is cosh a, and when x is 0, that means u is cosh 0. But because cosh, and I'll put the formula properly on the board in a second, but I think it's e to the a plus e to the minus a over 2. Of course, those things will just add to make 1 plus 1 over 2, because I'll put the formula up in a second. Anyway, but cosh 0 is definitely 1. And yeah, we put this in, like I said, the shines cancel, which is super useful. And then we can break this 2u squared minus 1 up into partial fractions, or, well, factorize it first, to then put it in partial fractions. You could do this properly, but I was just aiming to spot it. So like if I know it has to be a minus, because then I can get the root 2u's to cancel if a and b are just equal to each other when I put them together. But currently I've got 1. Assuming a and b are 1, I would have 1 minus 1 is 2, and I only want a 1, so I'm just going to halve them both. As long as they're the same, the u's will still cancel out, but the 1's this time will actually halve as well to a 1. So that's nice. So this is definitely it. And I was just being a bit lazy there. If you want to do partial fractions properly, go ahead and do that. At this point, you can just integrate, because these obviously integrate to logs. The half comes out front, but also this differentiates to root 2, so that needs to come out front as well down there. And we get those two integrals there, so that's nice. And then we put in our limits, I guess. I've combined the two logs, sorry, I should say. This one over this one, because, of course, log laws. Then we can put in the coshes, and we can also put in the 1 to get this thing here. And this thing here just needs to try and make it look like the question, right? So how do we do that? Well, this thing here flipped over is this thing here. So that's going to be this to the power minus 1 is going to be, yeah, or do it this way. Put the minus 1 there first, and then you can flip it over. Sure, same thing. And we'll have our answer just there. So that's the first part done. And then it says, and also find this integral here. So we're just going to do the same thing, just with a shine as our substitution rather than a cosh, because also now when we differentiate this, we'll cancel this cosh. So that was the idea there. Replace the limits. Shine of 0 is 0, or shine, however you say that, is 0, because it's e to the x minus e to the minus x, so the top line cancels when you put in 0. Now cancel this, and now this is actually different, right? Because this doesn't break up into, this doesn't factorize, right? So it's not going to break up and then do partial fractions, but it is just one of the ones in the formula book. It's this one here, it goes to arctan. A is clearly just going to be 1, the coshes cancel, and then we can sort of factorize out this square here to make root 2u squared, so this x is behaving as root 2u. So we just put a root 2u in there in our integral, and then we put the limits in, and we should be fine. Putting in 0, arctan of 0 is just 0, so that's fine, and that will be good to go, and that is our answer just there. And it says hence show this thing here, so clearly hence means use these two things here. I noticed that if I did this one, take away this one, I would get cosh minus shine, but the denominators are different, so you can't just put the fractions together. This denominator is this one, but not this one. Or is it, though? Because we can just write, let's start here. Cosh squared is 1 plus shine squared, and then we expand the brackets out, and then we cancel, and we get this denominator here. So these denominators were the same all along, right? And so what we can do is, if we call that one I and that one j, this integral here is, well, it's not quite because of the limit, but we'll deal with that in a second. We're just doing j minus I here, right? So if we call this the integral k is the integral up to a, I guess. K is just j minus I, so I'm defining k to be the integral between 0 and a. And it's just this answer here, right, minus this answer here. So I've just done that, take away that. But of course, if we call this integral L, L is just the limit of as a tends to infinity of k, right? K is what happens when the upper limit is a. We're just going to send that to infinity. So look at this line here and just send all the a's to infinity. So I said I would bring out the shines and the coshes, which here they are. If you send a to infinity, that becomes infinity minus 0. So this just becomes infinity. Arctan of infinity, we can kind of just say is pi over 2. So this becomes pi over 2 in here, over root 2. So that becomes that there. Then this one here, cosh, as a goes to infinity, becomes infinity again. But that just essentially makes this whole thing 1, because the top and the bottom are basically the same when cosh is really, really large. So this is log of 1, which is 0, so that whole thing goes away. And then here, of course, that's got nothing to do with a, so we keep it. and we end up with the answer that they wanted us to get just here. So that's all good. So we've shown this by substituting this into this result. Okay, show or find this result here. Okay, well, let's do that then. So let's say du equals e to the x dx, obviously. Now I can also say that as x goes to infinity, u also goes to infinity based on this result, and as x goes to 0 or is 0, u must be 1 because e to the 0 is 1. Now we can also say e to the minus x is 1 over u just from this result here. And that's useful because when we're putting this all in here, so the limits are what I said they were. Dx is e to the minus x du, which is 1 over u du. And then all of these things come from this over here. So cosh x is e to the x plus e to the minus x over 2. But e to the x is u, and e to the minus x is 1 over u, or u to the minus 1 is how I've written it here. Likewise with shine, and then shine again down here, or square. And now you've just got a bunch of algebra to do here, right? So the u over 2's minus u over 2, they cancel. So we end up with u minus 1 minus u minus 1, so that's just one copy of u minus 1 because of the halves. And then this down here, I've just expanded out. This becomes a 4 on bottom, times by 2 becomes a half. And then we just do a little bit more work, we get to there. And now, of course, we can just times by u squared, that comes from this u and this u together to make this one down here. Factorize out the 2, which is essentially what this half is actually at 2. And we get this here, which is the result that they're sort of talking about. But of course, that's equal. Our original integral I is equal to 2 lots of that result. So therefore, we just need to divide our original answer by 2, and we'll end up with a result for that. Now, that was a really nice question. And then it said at the end of this question in the booklet, you might want to look at 2004 step 3 question 2, which is similar to this one. So bonus step question alert, bonus step question alert. So we're going to do another step question. And looking at this, it does look rather similar, particularly this last result down here. Wouldn't you know, solving step questions makes you better at doing other step questions, because sometimes not only just getting the general practice of maths down, but sometimes they apparently ask pretty much the same thing, just in a slightly different way. So okay, let's do a substitution here. U equals cosh x. This all looks very similar to what we did before. I can write cosh 2x as this first, and then I can change it into basically either one of the denominators we were dealing with earlier. But at this point, this is now the same as part 1 from what we did before, because I can just make the substitution cosh x. U equals cosh x. It cancels the shine, and the working is identical, except for the fact, of course, that it's an indefinite integral. So we just have a plus c at the end, and we're all good to go. And then it says use a similar one here. Again, we can do basically the same. Make the denominator the other thing that we had in part B, I guess, because now we can make the substitution u equals shine x as we did before. It's all exactly the same, and we end up with the same answer, just with a plus c, because again, it's indefinite. As before. And now it says, using these parts to show this thing here. Now, just notice that this question is, in some ways, I guess, arguably significantly harder than the one we just did, because they don't tell you what substitution to make. And it might not be very easy to spot if you're not told. But of course, we can cheat because we know exactly what substitution to make. And we also know exactly what to do. We do I minus j, because that's what we did in the last question. And then we make the substitution u equals e to the x, right? And this is definitely going to work. Because it's basically just the same thing from this point onwards. So we do this, we can pull out the minus 2 from down there, we can put those u's together, we can times, and we get this here. But that, of course, is equal to I minus j, and we have the answers to I minus j. This is it, I minus j plus some other constant, I guess, is equal to this, divided by minus 2, and we end up with this here. And now when we put the limits in, the constant goes away, because we no longer care about constants when we're doing definite integration. And we just need to think about what those limits are. So when we have an upper limit when u is 1, looking at the substitution I made, when u is 1, x is 0 because it's log of 1. And when u is 0, we can say x is kind of minus infinity, because if you imagine the log graph, it goes down to minus infinity there. So those are our 2 limits. And now, not too trivial to put these limits in, right? When you put in 0, shine is 0 of 0 is 0, arctan of 0 is 0, so that term goes away. When you put in 0 here, cosh of 0 is 1. So that just makes this whole thing there, just without those 2 things. That's fine. And then we put in minus infinity, slightly more tricky again. Shine of minus infinity. Did I bother writing the shine thing down? No, I didn't. Pretty dumb. It's actually, I think, minus infinity, and then arctan of minus infinity, you can kind of say is minus pi over 2. And then put these in, and then here, cosh of minus infinity is, I believe it's, I think it goes to infinity again, because it's e to the minus infinity plus e to the minus infinity, so it goes to infinity. And then, but of course, that just makes this whole thing log of 1, as we kind of saw before, which is 0, so that whole time goes away. And this is nearly what they want us to get, except not quite. There's a bit of trickery involved here. This is all pluses, so let's get rid of this minus by putting it up there, and then turning this thing over to make this. And now this, I think we can rationalize by timesing it by this, which makes this. Of course, don't bother expanding this out, because you notice at the top here, you just want that thing with the 2 there that will come down there, and that's exactly how we're going to deal with this. So we'll put that 2 down there. We'll factorize out the 1 over 4 root 2, and we'll have it exactly as they want it. So that's that question done as well. And now we'll get to the second question from the booklet, which is such a great question. These are all our integrals here, and we just need to show that they're all equal to each other without actually working out any of them. So clearly there's just a bunch of substitutions going on to try and make these different things look different and make all the limits different, except these 2 limits are actually the same. So I mean, this minus arguably swaps them over, I guess, but let's just work on the basis that these 2 don't need a substitution to get from one to the other, because the limits are already the same. How would you then get from one to the other without one? Well, what you could do is you could integrate by parts, because integrating by parts still gives you another integral at the end of it. So let's take t. Oh, by the way, the thing talked about how when this question was done for real, you had a formula booklet, so it's likely the case that they would give you, if this question was asked now, the really useful ones from here that they thought you might need, rather than making you know them. It was just a quick note that they might have done that. Anyway, these are the 2 that we really need, because what I'm going to do is I'm going to work with t here, and I'm going to do integral by parts, because I can integrate t to the power minus 1 to log t. So I'm going to do that, integrate it here, leave this one alone here, and then differentiate it over there, and the differential of arctange is this thing here. So that's cool. And then this thing here, if we notice, is basically v. We'll apply the Taylor-Swift law of definite integration in a second to make sure it definitely is v. But here, we need to evaluate this thing here, and basically we need to hope it's 0. So we put in the half, we put in the third, and then this thing is also useful. This is a definition to do with arctange that's to do with logs. So let's replace those with that definition from up here. And what we can notice if we sort these 2 things out over here, is, of course, 1 plus is 3 over 2. That's a half. That's 4/3. That's 2/3. All of the halves and the thirds cancel to get you this. And now this here is minus log of 2. That's this is minus log of 3. So those 2 signs swap, but now these 2 things are identical, so they all cancel, and we just end up with this thing here. And now by the Taylor-Swift law of definite integration, which is the integral between a and b of f or a function of Taylor-Swift integrated with respect to Taylor-Swift, is just the integral of any the function defined in any other variable with the integrated with respect to that variable. So we can now change this t, all these t's actually, to be v's, and that's exactly what v is, and therefore we have that t and v are definitely equal to each other. Okay, and then I tried to get to u and x, and now I can go from either one of these to get there. But what I thought was from t to u, halves and thirds and logs and log 3s and log 2s, they're kind of related. So I was trying to get from t to u, and I thought, okay, well, if you use like something like t equals e to the u, if you use t equals e to the u, then what happens is when t is a half, you get u is log of a half. But that's minus log 2. And I didn't really want minus log 2s. I wanted plus log 2s and plus log 3s. So I decided to go with a minus u in here as well, hoping that that minus would then change these to be positives as well. So that was my plan. So I went with that. I differentiated to get this, and then I threw that result into here. All into here, obviously. Threw it all into there. So when t is a half, just to recap, you get log of a half is minus u, which means minus log of a half is u, but minus log of a half is log of 2, right? By power laws for logs. We saw it in the previous couple of slides. So that was my logic to get this one here, and these log 2s and log 3s. Now, I'm not concerned that these are all around, because I can just spend a minus to flip them over to get back to here. So that's why I'm not concerned about that, just in case I wasn't clear about that. Not concerned about that. Let's put these 2 things in here, and again, I've used the arctange formula that they gave me up here very usefully for this there. Now, these things obviously cancel. This minus is amazing because it does exactly what I wanted, which is flips those logs over. So now I've got the logs looking like u, which is fantastic. And now what do I do with this? Because it was at this point that I realized, well, I'm actually getting closer towards x by mistake than I am towards u. So, okay, let's can I try and get to X then? How would I get to X? And I've seen this trick quite a few times in the complex number booklet and some other booklets that we've done in step 3. But if we factorize out e to the minus a half u from top and bottom here, that ends up getting this thing here, which looks like complete nonsense. Of course, this cancels, which is great. This looks like nonsense until you realize that it's actually just the sinh and cosh things that you had before. You've got essentially, this is cosh divided by sinh. Now you're missing the 2's, but that doesn't matter because they would cancel anyway when you divide. So this here is definitely coth, because it's cos divided by sine. So this is definitely coth of a half u, because that's the input in here. So that's coth of a half u. And now, okay, this is looking very close. I think if I just make a very quick substitution, this will be exactly right, because the half will cancel with the 2, and that will be fantastic. And we'll end up exactly what we wanted. And now at this point, of course, we use the Taylor-Swift law for definite integration again, which is log of coth of Taylor-Swift with respect to integrated with respect to Taylor-Swift is the integral of log of coth of s ds, as long as the limits are the same. And well, that's of course the same as when you put x's there, and of course x has x's in it. So of course that's also equal to x. And now we have that t is equal to v, but also equal to x. So the only one left was u. And I decided to get to u, well, if I went from t to x, maybe I should go from v to u. Maybe that's the way of getting there from there to there. So I used the same substitution, actually, exactly the same one for the exact same logic that I had before. Again, I'm not concerned about this minus, because all that does is swap these two things over, which is great because I want the thing to do with 3 at the top anyway. So I used exactly the same substitution trying to get from here to here. And it actually works out pretty well, as you can probably tell. So the limits work out the same as they did before. This e to the u doesn't cancel this time, but that's okay. Of course, log of e to the minus u is just minus u. You actually, this minus, I used this minus, I guess, to swap these limits. And then this minus just has to go at the front. But you get another minus from this whole log e cancelling with a minus u there. So you get another minus there, which will cancel that minus as well. So you're just left with this. And now how do you deal with this? How do we try and make it look like this? Well, again, it's a case of doing a very similar thing to what we just did, which is factorize out e to the minus u from this bottom row here. Because not only does it cancel with the e to the minus u above it, but also you get left with this, which I think is just precisely 2 shine a, or 2 shine u, I should say. And then because I just chose to use u as my substitution letter, I'm precisely already at the integral u. I don't need the Taylor-Swift law. But I decided to, because I obviously solved this and was very happy, I decided to find a bunch of pictures of Taylor Swift looking very happy and proud of me. So we've got those to enjoy as well. Thank you so much for watching, and I'll see you next time.